Here's the formula for the sum of the first n cubes. It claims this sum equals the square of the nth triangular number. We're tasked with proving this relationship holds for all positive integers. And if you stick around until the end, I'll show you an entirely different and arguably more elegant way to prove this. To accomplish this, we'll use the principle of mathematical induction. This method is like climbing a ladder. First, we show we can get on the first rung, then we show that from any given rung, we can always climb to the next one. Together, these two steps prove we can climb the entire ladder. First, we establish our base case. We need to verify the formula holds for the very first step, where n equals 1. We substitute n equals 1 into the original statement. The left side is simply 1 cubed. The right side becomes 1 squared, times the quantity 1 plus 1 squared, all divided by 4. Let's evaluate both sides to confirm they're equal. 1 cubed is 1. On the right, 1 plus 1 is 2. Now, let's simplify the right-hand side. 2 squared is 4, and 4 divided by 4 is 1. The statement holds true. Our base case is secure. Next, we make our inductive hypothesis. We assume the statement is true for some arbitrary positive integer, which we'll call k. This assumption is the critical rung on our ladder, the one from which we'll attempt to climb to the next. Now, for the crucial part, the inductive step. We must prove that if our Sig's hypothesis is true for k, then it must also be true for the next integer, k plus 1. This is our goal. We need to show that the sum up to k plus 1 cubed equals this expression on the right. Let's simplify the expression on the right side to clarify our target. So our objective is to show the left side simplifies to the quantity k plus 1 squared times the quantity k plus 2 squared, all over 4. We begin with the left-hand side of the statement for p of k plus 1. Notice that this part of the expression is exactly what we defined in our inductive hypothesis. Therefore, we can substitute the right side of our hypothesis for this entire sum. To combine these terms, we need a common denominator. We express the second term as a fraction over 4. Now that both terms share the same denominator, we can combine them into one fraction. We add the numerators over the common denominator. Observe the common factor of k plus 1 squared in the numerator. This is the key to simplifying the expression. Factoring this out is the pivotal step. Now, let's simplify the expression inside the brackets. We distribute the 4. This quadratic expression is a perfect square. K squared plus 4. K plus 4 factors into k plus 2 squared. This result is identical to the right-hand side of our goal statement for p of k plus 1. Let's summarize our findings. We've shown the base case holds, and we've shown that the truth of the statement for any integer k implies its truth for k plus 1. By the principle of mathematical induction, the formula is proven for all positive integers. Now for a different perspective. Induction is rigorous, but not always the most direct path. There's another method that leverages a remarkable mathematical identity. This is Nicomachus' theorem. It states that the sum of the first n cubes equals the square of the sum of the first n integers. And we know the formula for the sum of the first n integers. The nth triangular number is n times n plus 1, divided by 2. With these two facts, our proof becomes a simple substitution. We replace the sum of the integers in Nicomachus' theorem with its known formula. Now all that remains is to square the expression on the right. And this gives us the original formula. This proof is much faster, but it relies on knowing two other significant results. Induction, while longer, builds the proof from the ground up. Two different paths to the same mathematical truth. And that's the beauty of mathematics. Sometimes there are multiple elegant paths to the same truth. If you enjoyed seeing how induction and direct proof can both tackle this classic result, consider giving this video a like. And if you want to see more mathematical insights like these, subscribe for more explorations into the elegant structures of mathematics.